Welcome to The Deep Dive. We're the show that loves digging into complex stuff and pulling out the key insights for you.
That's right.
Today, we are going deep, really deep, into the heart of modern flight itself, the gas turbine engine.
It's quite a topic. These engines, they're not just big, complicated machines you see hanging off wings.
No, they're absolute marvels of engineering.
Yeah.
Powering everything from, jumbo jets to helicopters.
And yeah, they might seem incredibly complex, maybe even a bit intimidating.
Definitely. But understanding how they work, it's actually surprisingly within reach, especially if you've got that curious spark.
And that's exactly what we're aiming for today. Our mission, if you will, is to give you a really solid foundational understanding of these power plants, not just like surface level facts. We're drawing heavily from a fantastic resource today. It's designed specifically for folks training to be aircraft maintenance technicians. It's the EAA Part 66 Gas Turbine Engine Module 15. Very detailed stuff.
So think of this as your personal guided tour, a shortcut maybe, to getting genuinely well-informed about these mechanical titans.
Yeah, we want to explore not just what they are, but the really fascinating how and why behind their operation.
The fundamental principles, the things that actually let these massive machines defy gravity day in, day out.
Exactly. So whether you're maybe studying for your EASA exams, or you're just a huge aviation enthusiast,
Or maybe you just love taking complex systems apart in your head.
yeah, then this deep dive, it's really tailored for you. Get ready for some, hopefully some serious aha moments as we decode that roar.
All right, let's jump right in. To really get how these engines fly, we have to start with the basics. The foundational science, the essence of thrust.
It really does come down to fundamental physics, and the most direct one here is Newton's third law of motion.
The classic. Action-reaction.
The very same. For every action, there is an equal and opposite reaction. Think about it. The engine blasts this huge volume of hot gas backwards at high speed.
Right.
That's the action. And the reaction, the engine and the whole plane attached to it gets pushed forward. It's a constant push, turning that backward blast into forward motion.
It sounds so simple when you put it like that, but scaling that up to lift, hundreds of tons, that's where the magic is.
It is. It's elegant physics. But it's not just that it pushes gas out, it's how much gas and how fast it pushes it.
Right, the force involved.
Exactly. And that brings us straight to Newton's second law. Force equals mass times acceleration. FMA.
The formula that lets us actually put a number on the engine's power, the thrust.
Precisely. We can calculate it. The formula often looks like force equals the mass flow rate of the air times the change in velocity, so the exit speed minus the inlet speed.
Okay.
Sometimes you see it written as F of d F era v g t, where W is weight flow rate and G is gravity, or using mass flow, FM's V2 V1 G.
Is there an example in the source material? Numbers always help.
Yes, there's a good one. Imagine a turbojet engine, a simpler type, and it's moving 150 pounds of air through its core every single second.
That's a lot of air.
It is. Now, say that air comes in at maybe 100 feet per second. Pretty slow.
Okay.
But it gets blasted out the back at 1,200 feet per second.
Wow, big difference.
Huge difference. You plug those numbers into the formula, and that engine is generating 5,124 pounds of thrust. That's the kind of force we're talking about.
5,000 pounds.
Yeah.
Just from accelerating air. That's impressive. And just a quick clarification point, because it trips people up sometimes.
Go ahead.
When we say FMA, the M is mass.
Yeah.
Right? The amount of stuff. Not necessarily weight, which is gravity's pull on that stuff.
That's a really important distinction, especially in aviation. Mass is constant, but weight changes with gravity, like at altitude. At sea level, a pound of mass weighs a pound, but they are technically different concepts.
Yeah. Okay, so we have the force. What about the energy side of things? How does that play out inside the engine?
Right. Energy transformations are happening constantly. We're mainly dealing with two types, kinetic and potential energy.
Kinetic energy, that's the energy of motion, right? Like plane rolling down the runway or the part spinning inside the engine.
Anything moving has kinetic energy.
And potential energy, that's stored energy.
That's the one. Stored energy, ready to do work. Think of water behind a dam.
Or, more relevant here, the chemical energy locked up in jet fuel.
Precisely. Huge amounts of potential energy sitting in that fuel.
And interestingly, the source notes, they share the same units, foot-pounds or inch-pounds, in the English system.
Yeah, it shows they're fundamentally related, both measures of work potential.
So how do these two connect inside the gas turbine?
It's a continuous conversion process. The engine is constantly taking the chemical potential energy in the fuel, releasing it through combustion, turning it into the kinetic energy of those hot, expanding gases.
Right.
That kinetic energy then spins the turbine, which is mechanical energy,
Which drives the compressor.
and ultimately produces thrust. It's this nonstop energy chain reaction, all governed by the laws of thermodynamics.
Amazing efficiency. And speaking of efficiency in handling air, Bernoulli's principle comes up a lot. How does that influence engine design?
Bernoulli is crucial. It basically says when a fluid and air is a fluid speeds up, its pressure drops, and vice versa.
Okay.
Engineers use this everywhere. Take convergent ducts that get narrower.
Like the exhaust nozzle.
Exactly. As the hot gas gets squeezed through that narrowing nozzle, it speeds up massively. Bernoulli says its pressure must drop. That high-speed, low-pressure exit maximizes thrust.
So you're trading pressure for speed at the very end.
Mm-hmm.
Makes sense. What about the opposite? Wider ducts.
Those are divergent ducts. They get wider. You find them in places like the compressor inlet and the diffuser section, just after the compressor.
And they do the opposite.
Precisely. They slow the air down, and as the air slows, its pressure increases. This pressure rise before combustion is absolutely essential for efficient burning.
So you're carefully speeding up and slowing down the air at different points using the shape of the ducts?
It's all about manipulating velocity and pressure using geometry, all thanks to Bernoulli.
The source also mentions Boyle's and Charles's law briefly. They relate pressure, volume, and temperature of gases, right?
Yes, they're the fundamental gas laws. While Bernoulli describes the velocity-pressure relationship in flow, Boyle's and Charles's laws explain how the temperature, pressure, and volume of the air itself change as it goes through compression and heating. They underpin the whole thermodynamic process.
Got it. Okay, so we have thrust, energy, airflow principles. Let's tie it all together with the engine's core operating cycle. Its metabolic process, as the outline calls it, the Brayton cycle.
The Brayton cycle. That's the thermodynamic cycle for gas turbines, sometimes called the continuous combustion cycle.
Continuous being the key word there, unlike, say, a car engine.
Exactly. In your car's piston engine, intake, compression, combustion, exhaust happen one after another in the same cylinder. It's intermittent.
Right. Bang, bang, bang.
But in a gas turbine, all those things, intake, compression, combustion, exhaust, are happening simultaneously, continuously, but in different sections of the engine.
Ah, that's the big difference. Separate departments for each job, all working at once. Like an assembly line.
That's a great analogy. It allows for much higher power output and efficiency for the engine size. Let's walk through the 4 continuous events.
Okay, step 1, intake.
Air comes into the engine inlet at whatever the outside pressure is. But here's something interesting. The ram effect.
The plane moving forward forces air in.
Pretty much. Especially at higher speeds, the air gets slightly compressed just by being forced into the inlet. So it leaves the intake section with slightly higher pressure and lower volume than the outside air.
Okay, a little pre-compression just from moving, then the real work starts.
Then comes compression. Big time. The compressor section mechanically squeezes that air, massively increasing its pressure and decreasing its volume.
This takes a lot of the engine's own power, right?
A huge chunk, yes. Compressing air efficiently is hard work.
Okay, highly compressed air, now what?
Now, the expansion, or power phase, this happens in the combustion chamber.
Where the fuel gets added and burned.
Right. Fuel is sprayed in, ignites, burns incredibly rapidly. This heats the air intensely, causing it to expand dramatically. Now, the pressure stays relatively constant through the combustion chamber,
Okay.
but the volume increases hugely. This high-energy, high-volume gas then rushes towards the turbine.
And that's what spins the turbine.
That's what drives the turbine, converting that heat energy back into mechanical work to spin the compressor and run accessories.
And finally, the last stage.
Exhaust. The remaining hot, high-pressure gas flows out through the exhaust nozzle. The nozzle converts that remaining pressure and volume into a high-velocity jet stream.
And that high velocity is the thrust, back to Newton's third law.
Exactly. That continuous flow intake, compress, burn, exhaust, all at once is what gives turbines their amazing power-to-weight ratio.
Incredible. Now, when we talk about how much power, we need specific metrics. How do we measure or rate a turbine's power compared to, say, a piston engine?
Good question. Piston engines are usually rated in brake horsepower, BHP, power available at the shaft. Turbines are different. We often talk about thrust horsepower, THP.
Thrust horsepower, how's that calculated?
You take the thrust the engine produces in pounds, and multiply it by the aircraft's speed in miles per hour, then divide the whole thing by 375.
Okay, so thrust times speed divided by 375. Is there an example?
Yeah. Say an engine makes 4,000 pounds of thrust and the plane is flying at 500 miles per hour.
Okay.
You multiply 4,000 by 500, that's 2 million, divide by 375, and you get about 5,333 THP.
Wow. That's a lot of horsepower. But you said it depends on speed.
Critically depends on speed. If that same engine is sitting still on the ground producing 4,000 pounds of thrust, its speed is 0, so its THP is 0.
Okay. So THP isn't a fixed value like BHP. It changes with flight speed. Makes comparing them directly tricky.
Very tricky. That's why thrust is often the more fundamental measure for jets. Another key metric is efficiency, specific fuel consumption, SFC.
How much fuel it burns to produce a certain amount of thrust.
Exactly. It's defined as fuel flow in pounds per hour divided by thrust in pounds. Lower SFC means better fuel efficiency.
And how do different engine types compare on SFC?
It depends on speed again. At lower speeds, say below 400 mph, per hour, piston engines, and especially turboprops, are generally more fuel efficient. They have lower SFC.
Okay.
But as speeds get higher, propellers lose efficiency rapidly. Above 400 mph or so, turbofans really start to shine and become more efficient. Their SFC gets better relative to props at high speed.
So it's all about matching the engine design to the typical operating speed. Makes sense.
It's always a trade-off.
Beyond thrust and fuel burn, what are the other big picture requirements for these engines? It's not just about power, is it?
Oh, definitely not. General engine requirements are extensive. Obviously, efficiency and a good power-to-weight ratio are key.
Lighter is better?
Always in aviation. Reliability is absolutely paramount. They need to run for thousands of hours between overhauls, delivering sustained high power. Durability is crucial.
Makes sense.
They also need to be compact, affects aerodynamics, pilot view, weight. They need to be as vibration-free as possible. And flexible, able to operate reliably across a huge range of speeds and altitudes.
So the fuel system, oil system, everything has to work perfectly, from sea level to 40,000 feet, hot or cold.
Exactly. It's an incredibly demanding set of requirements.
Okay, with those fundamentals covered, let's dive into the engine itself. Section 2, the core anatomy. What are the main sections we need to visualize?
We can break it down into about 7 key functional areas. You've got the air inlet.
Where the air comes in.
Right. Then the compressor.
Squeezes the air.
The combustion section.
Adds the fuel and fire.
The turbine section.
Extracts power to drive the compressor.
The exhaust section.
Directs the thrust out.
Then you have the accessory section, usually a gearbox driving pumps and generators. And finally, the essential systems woven throughout starting, lubrication, and fuel systems.
And the key thing, as you said earlier, is that all these sections are working at the same time.
Simultaneously and continuously. Unlike a piston engine cycle, that simultaneous operation is fundamental to how they work and why they're so powerful for their size.
Amazing. Let's start right at the front then. The air inlet, the engine's gateway. What's its job beyond just letting air in?
Its main job is to efficiently gather enough air and, crucially, deliver it to the compressor face with as little turbulence or distortion as possible.
Why is smooth, undistorted airflow so critical right at the start?
Because the compressor blades are very sensitive airfoils. If the air hitting them is swirling or uneven, it dramatically reduces the compressor's efficiency. It can lead to excessive temperatures downstream, or even worse, compressor stall.
Okay, so a good inlet sets the stage for the whole engine.
Absolutely. You mess up the inlet, you compromise everything after it.
And inlets look really different on different planes. Why the variety?
Designs are tailored to the aircraft's role. Turbofan inlets on airliners are usually simple, fixed, bolted to the front. They often have acoustic linings inside.
To reduce noise.
Exactly. Sound-absorbing materials help quiet down the fan noise, which is a major component of overall engine noise on those big bypass engines. Many also have inlet guide vanes, or IGVs.
Stationary blades.
Right. Fixed airfoils right before the first rotating fan blades. They help straighten the incoming airflow, ensuring it hits the fan blades at the optimal angle.
Okay. What about turboprops or helicopters?
Turboprop and turboshaft inlets can be more complex. They might have screens to stop debris, FOD, foreign object damage, or special vanes to deflect ice particles. Heated inlet lips are common to prevent ice buildup. Their airflow needs are a bit different too.
And military jets, especially supersonic ones, their inlets look really complex.
They are. Supersonic inlets have a huge job. They need to slow down air traveling faster than sound before it enters the engine.
Why? Can't the engine handle supersonic air?
Absolutely not. Supersonic flow inside the compressor or turbine would create shock waves that would basically destroy the engine components. So these inlets use complex shapes, sometimes with moving ramps or cones, to create a series of controlled shock waves that slow the air down to subsonic speeds below Mach 1 just as it reaches the engine face.
That's incredible aerodynamic juggling.
Really is.
Any specific inlet types used for testing or maintenance?
Yeah, during engine testing in a test cell away from the aircraft, they often use a bell mouth inlet.
What's that?
It's a large, smooth, bill-shaped inlet. Its shape provides almost perfectly smooth, undisturbed, zero-resistance airflow into the engine.
Why use that?
It allows engineers to measure the engine's true performance, like its maximum rated thrust or its specific fuel consumption, without any losses or distortions caused by the aircraft's own inlet duct. It gives you a clean baseline measurement.
Gotcha. It isolates the engine's performance.
Precisely. And it highlights again how even small inefficiencies in the real-world aircraft inlet can really add up and affect overall performance.
Okay, air is smoothly in. Now it hits the compressor section, the air squeezer. What's its core function?
Simple goal. Supply enough air at a significantly increased pressure to the combustion section. It packs the air molecules closer together.
And each stage of compression gives a pressure boost.
Exactly. A compressor stage typically involves a row of rotating blades followed by a row of stationary blades, and each stage adds a bit more pressure.
And there are two main types, right? Centrifugal and axial.
That's correct. Let's start with centrifugal flow compressors.
How do they work?
Think of a spinning disc, the impeller flinging air outwards using centrifugal force. The air picks up speed, then it hits a stationary diffuser section around the edge.
And the diffuser.
The diffuser slows the air down, converting that high speed into high pressure. Then a manifold collects the compressed air.
What are they good at?
They can achieve a high pressure rise in a single stage, maybe 8-to-1 compression ratio. They're also relatively robust and simpler, but they're not very efficient if you try to stack multiple stages.
So where do you usually find them?
Mostly in smaller engines, like turboprops, turboshafts for helicopters, and APUs, auxiliary power units. The impeller is often made from a strong, lightweight material like forged aluminum alloy.
Okay. And the other type, the one we see on big jets?
That's the axial flow compressor, much more common in turbofans and turbojets.
How does it work differently?
Here, the air flows straight through, along the engine's axis, hence axial. It passes through multiple alternating rows of rotating blades, rotors, and stationary blades, stators.
Rotors and stators.
The rotor blades act like tiny propellers, pushing the air backward and speeding it up slightly. The stator blades then act like diffusers, slowing the air down and converting that velocity into a pressure increase.
And each rotor-stator pair is a stage.
Correct. Each stage only gives a modest pressure increase, maybe 1.25 to 1 ratio.
That doesn't sound like much.
Per stage, no. But the advantage is you can stack many stages, 10, 15, even more, one after another. So the total pressure rise across the whole compressor can be huge, like 30-to-1 or even higher in modern engines.
Ah, I see. Lots of small steps add up to a big result. What are these blades made of? They must be strong.
Very strong. Rotor blades are often stainless steel, especially in the early stages. In the later, hotter stages, they might use titanium alloys. Stator vanes are similar. They need to withstand high temperatures and stresses.
And how are they attached to that fir tree thing?
Yeah, the attachment method is critical because of the huge centrifugal forces. The root of the blade is often shaped like a fir tree or sometimes a bulb. This shape slots into a matching groove in the compressor disc, providing a very strong mechanical lock.
Clever design. Now, compressing air that much sounds tricky. What can go wrong? Stall and surge.
Those are the big operational challenges. Compressor stall and surge. Remember, each compressor blade is an airfoil, like a tiny wing.
Okay.
A stall is when the airflow separates from a blade, or a few blades in one stage. They lose their lift or ability to push air effectively.
Like a wing stalling on a plane.
Similar principle. Now, a surge is much more serious. That's when the entire compressor experiences a breakdown in airflow. The flow can actually reverse direction momentarily. It's violent.
Yikes. What causes that?
Several things. High crosswinds on the ground, maybe ice ingestion, the pilot moving the throttle too quickly.
Slamming the power on or off?
Exactly. Sharp aircraft maneuvers can do it too. Or internal issues. Maybe the fuel control isn't responding correctly, or the blades themselves are damaged or dirty. Even malfunctioning airflow control systems within the engine, like bleed valves not opening when they should, can trigger it.
How would you know it's happening? What are the signs?
You'd likely hear it first. Abnormal noises, rumbling, maybe a loud bang or a series of bangs.
Not good sounds from an engine.
Definitely not. You'd also see rapid fluctuations on the cockpit instruments, RPM, EGT, exhaust gas temperature, EPR, engine pressure ratio, would all be jumping around erratically, and the engine wouldn't respond properly to the throttle.
And the effect on the engine itself sounds damaging.
Extremely damaging. The shock loading can fatigue components. The rapid temperature spikes, especially the EGT during a surge, can seriously exceed the design limits of the turbine section downstream. Even one bad surge event can drastically shorten the engine's life.
Wow. Okay, so smooth airflow is key. Assuming the compressor does its job, where does that high-pressure air go next?
It flows into the combustion section. This is where the heat gets added. The fire is contained, as the outline says.
But it's more than just a fire pit, right? It has specific jobs.
Absolutely. Its functions are critical. Efficiently burn the fuel-air mixture at a tremendous amount of heat energy. Then, and this is crucial, the resulting gases down significantly before they hit the turbine.
Cool them down. Wait, why?
Because the temperatures right in the flame can reach maybe 3,500 degrees Fahrenheit. That's far too hot even for the exotic metals in the turbine. So the combustion section has to mix in cooler air to bring the temperature down to something manageable, like 1,500 degrees hour or so, before it enters the turbine.
Ah, okay. Tempering the inferno and delivering the hot gas smoothly.
Yes, delivering a uniform flow of hot gas to the turbine nozzles is the final job.
What are the basic parts you'd find in any combustor?
You'll always have an outer casing to handle the pressure, a perforated inner liner where the burning happens, fuel injectors or nozzles, igniter plugs to start the fire, and a drain system.
Let's talk about airflow inside. You mentioned cooling air. How is the air managed?
It's very clever. Only a portion of the air coming from the compressor actually mixes directly with fuel for burning. That's called primary air.
Okay.
The rest, the secondary air, is used for cooling and shaping the flame. Some flows between the outer casing and the inner liner, cooling the liner walls.
Like a jacket of cooler air.
Exactly. Then it enters the main combustion zone through carefully placed holes further downstream to mix with the burning gases and cool them down before they exit. There are also tiny louvers or slots in the liner that bleed a thin film of cooling air along the inside surface, keeping the flame away from the metal walls.
Wow, intricate. And swirl vanes.
Yes, often placed around the fuel nozzles. They impart a swirl to the incoming primary air, which helps atomize the fuel spray and mix it thoroughly for efficient, stable burning.
Are there different designs of combustion chambers?
Yes, historically there were can-type combustors. Imagine several individual cans arranged in a circle, each with its own liner and fuel nozzle. They were connected by small tubes so the flame could jump from one can to the next during starting.
Okay, multiple individual burners.
Right. Then came the annular pipe. This is just one single, continuous donut-shaped liner encircling the engine shaft. More modern, generally lighter, and more efficient.
Like one big ring of fire.
Pretty much. And there's a hybrid, the can annular type. This has individual flame tubes or liners like the can type, but they are all housed within a common annular outer casing. Kind of combines features of both.
Interesting. And you mentioned a drain system earlier. Why is that so important here?
Absolutely critical for safety. After shutdown, there might be unburned fuel left in the nozzles or the bottom of the combustor. The drain valve allows this to escape.
Why is that bad?
2 reasons. 1, the fuel can leave gummy deposits if it sits there. 2, and much more dangerous, if that fuel is still there during the next start attempt, it can ignite uncontrollably when the igniters fire. That's called an afterfire or a hot start, and the resulting overtemperature can severely damage the turbine. Drains prevent that.
Makes perfect sense. Okay, so the now incredibly hot but slightly cooled high-pressure gas leaves the combustor. Where does it go?
It immediately slams into the turbine section. This is where the engine gets the power to sustain itself.
So the turbine's job is to extract energy from that hot gas.
Precisely. It transforms a large portion of the gas stream's kinetic and thermal energy into mechanical rotational energy. About 60 to 70% of the total energy released in combustion goes into driving the turbine.
70%. Just to keep the engine running.
Primarily to drive the compressor, which consumes a huge amount of power. On turbofans, it also drives the large front fan. On turboprops, the propeller. On helicopters, the main rotor shaft. Whatever's left provides the exhaust thrust.
Okay, so it's the engine's internal powerhouse. What are the key parts of the turbine section?
2 main elements. The stationary turbine inlet guide vanes, often called nozzle guide vanes or NGVs, and the rotating turbine wheel assembly.
Guide vanes first, what do they do?
They sit right after the combustion chamber, just before the first rotating turbine blades. They are fixed, airfoil-shaped vanes. Their job is to take that hot, high-pressure gas from the combustor and accelerate it, directing it onto the rotating turbine blades at the perfect angle for maximum impact.
And they get incredibly hot.
They are the hottest metal components in the entire engine. Their temperature is a major limiting factor for overall engine performance and life. Managing their temperature is critical.
Wow. Okay, so they aim the hot gas. Then it hits the rotating part.
The turbine wheel assembly. This consists of the turbine disc, which is the solid wheel, and the turbine blades attached around its rim. The disc is attached to the main engine shaft.
And blades catch the gas.
Exactly. The high-velocity gas flowing through the guide vanes strikes the curved turbine blades, forcing the entire wheel assembly to spin at extremely high speeds, tens of thousands of RPM.
Like a windmill in a hurricane. The blades must be under incredible stress.
Immense stress, huge centrifugal forces trying to rip them off the disc, plus the extreme heat which weakens the metal. They are truly engineering marvels.
Are they made and attached? Still using that fir tree method?
Often, yes. The fir tree root provides a very strong mechanical lock to the disc. They're made from exotic nickel-based superalloys, sometimes even grown as a single metal crystal to eliminate grain boundaries, which are weak points at high temperatures.
Single crystal blades, wow.
And many modern blades are hollow.
Hollow, why?
For cooling. Relatively cooler air bled from the compressor is ducted through intricate internal passages within the blade and exits through tiny holes on the surface. This creates a cooling film and allows the turbine to run much hotter than the metal's melting point would normally allow, often combined with special ceramic thermal barrier coatings on the outside.
That's incredible technology. Running hotter means more efficiency, right?
Directly translates to better efficiency and more power.
Are there different ways turbines are arranged?
Yes. Some have shrouded turbines, where the tips of the blades have interlocking seals that form a continuous ring or shroud. This can improve efficiency and reduce vibration.
Okay.
And very common in modern engines are multi-rotor or split-spool turbines. Remember the N1 and N2 spools we talked about with compressors?
Yeah, the low pressure and high pressure sections.
Right. Each spool has its own separate turbine stages driving it. So you might have a high-pressure turbine driving the high-pressure compressor, located right after the combustor. Then, further downstream, a separate low-pressure turbine on a concentric shaft drives the low-pressure compressor, and in a turbofan, the big front fan.
Why split them?
It allows each spool, compressor, and its driving turbine to rotate at its own optimal speed, which significantly improves efficiency across a wider range of operating conditions.
Very clever. Okay, so the gas has passed through the turbine, given up a lot of its energy. What's left?
What's left is still hot, still under some pressure, and moving fast. It now enters the final section, the exhaust section, the final push.
What's its main job?
To collect the gases leaving the turbine, straighten out the flow to prevent turbulence, and accelerate them through a nozzle to produce the final effective thrust.
The exhaust nozzle is key here.
Absolutely. Most common is a simple convergent nozzle, which narrows down. As we discussed with Bernoulli, this accelerates the flow and increases thrust.
Makes sense.
But for supersonic aircraft, you often see a convergent-divergent nozzle, or CD nozzle, also called a de Lava nozzle.
Convergent, divergent, how does that work?
It first converges, accelerating the flow up to the speed of sound, Mach 1, at the narrowest point, called the throat. Then the nozzle diverges, gets wider. In supersonic flow, surprisingly, expanding of the duct further accelerates the gas, so it can exit much faster than Mach 1, producing more thrust at high speeds.
Counterintuitive, but very cool. The shape of the nozzle opening must be critical then.
Extremely critical. The size or area of the nozzle exit determines the pressure and velocity relationships throughout the entire engine. Too big, and you lose thrust potential. Too small, and you choke the engine, restricting flow and potentially causing issues upstream like turbine overheating. It's precisely calculated.
Okay, that's getting the thrust out. But what about stopping?
Yeah.
Especially big, heavy planes, brakes aren't enough.
Not nearly enough, especially on wet or short runways. That's where thrust reversers come in, essential safety equipment.
How do they work? They actually reverse the engine's thrust.
They redirect it forward. There are two main types. Mechanical blockage types use physical doors or buckets that swing into the exhaust stream.
Like clamshell doors.
Exactly. Clamshells or blocker doors that redirect the flow through cascade vanes mounted on the outside of the nacelle. These are often used on engines where the fan air and core exhaust mix before exiting. They have to be strong, light, and absolutely fail-safe so they can't deploy accidentally in flight.
And the other type?
Aerodynamic blockage. This is mostly used on high-bypass turbofan engines, the big ones on airliners. These systems typically only redirect the fan air.
Just the air from the big front fan. Why only that?
Because on those engines, the fan produces the vast majority of the thrust, maybe 80% or more. Reversing just the fan air is highly effective.
How do they do that?
Usually, a section of the engine cowling, called the translating cowl, slides backward. This exposes a set of cascade vanes, and internal blocker doors swing out to block the fan duct's normal exit path. The fan air is then forced out through the angled cascade vanes, directing it forward and sideways.
So when the pilot pulls the reverse levers,
That sequence happens. Cowl slides, doors block, air redirects. Huge braking force.
sound like a lot of moving parts. Maintenance intensive?
Very. Lots of linkages, actuators, sensors. They require frequent inspection and lubrication.
Yeah.
And strict lockout procedures are essential during maintenance to prevent accidental activation.
Right, safety first. Now, the noise. Jet engines are loud. How do engineers tackle noise suppression?
It's a huge area of research. The main noise source is the high-velocity exhaust jet mixing violently with the surrounding still air. That creates the low-frequency roar. Fan and compressor noise contribute too, usually at higher frequencies.
So how do you quiet that roar?
One way is to change the shape of the exhaust nozzle. Instead of one big round jet, use corrugated nozzles, chevrons, you see them on many modern engines, or multi-tube nozzles.
Breaking up the flow.
Exactly. This breaks the single large jet into many smaller jets. It doesn't necessarily reduce the total noise energy, but it increases the frequency of the dominant noise.
Why does higher frequency help?
2 reasons. Higher frequencies are absorbed more effectively by the atmosphere, so the noise doesn't travel as far, and some of it gets pushed above the range of human hearing.
Clever.
So,
What about those acoustic liners you mentioned in the inlet?
yes, acoustic linings are used extensively, not just in the inlet, but also in the fan bypass duct. They're typically a layer of porous material over a honeycomb structure.
How they work?
They absorb sound energy. The sound waves enter the porous material and get trapped in the honeycomb cells, where their energy is dissipated as a tiny amount of heat through friction and viscous losses. Very effective, especially for fan noise.
But they add weight.
They do. That's the trade-off. Added weight and a very slight increase in fuel consumption due to the surface friction, but significant noise reduction.
Finally, briefly, what about engine emissions? Is progress being made there?
Definitely. Regulations are strict, and manufacturers are constantly innovating. A major focus is reducing no-NOx nitrogen oxides, which form at very high combustion temperatures.
Ow.
Newer combustor designs, like the TIPS combustor mentioned in the source, twin annular premixing swirler, focus on premixing the fuel and air much more thoroughly before they burn. This allows for a leaner burn, less fuel relative to air, which burns cooler and produces significantly less no-NOx. Also, just making the engine components more efficient overall reduces fuel burn, which cuts all emissions, including CO2.
Constant improvement. Okay, that covers the engine's main anatomy. Let's shift to the vital support systems in Section 3. These keep the core running. First, lubrication systems. The engine's lifeblood. What are the main types?
2 main types: wet sump and dry sump. Wet sump means the oil is stored within the engine itself, maybe in the accessory gearbox casing. It's less common in turbines now.
So most use dry sump.
Yes, the dry sump system is much more prevalent. It uses a separate external oil tank mounted on or near the engine.
How does the oil get around? What are the key parts?
You have the oil pump, which is critical. It's usually a complex unit with multiple pump elements inside. Some are pressure elements pushing fresh oil out to the bearings and gears.
And the others?
The others are scavenge elements. Their job is to suck the used oil back from the bearing compartments and return it to the tank.
Why separate scavenge pump?
Crucially, the total capacity of the scavenge pump elements is always greater than the capacity of the pressure element.
Why is that important?
It ensures that oil is constantly being removed from the bearing sumps faster than it's being supplied. This prevents oil from accumulating, foaming up, or causing excessive drag in those high-speed areas. It keeps the sumps dry, hence the name dry sump.
Clever. And keeping that oil clean must be vital. Filters.
Absolutely essential. Oil filters are everywhere. The main system filter removes very fine particles, down to maybe 25 or 35 microns. Remember, these bearings are spinning incredibly fast. Even microscopic debris can cause rapid damage.
What other filters are there?
There are often coarser screens called finger screens in the scavenge lines to catch larger debris. And critically, there are often last chance filters.
Last chance. Sounds important.
They're very fine mesh screens located right before the oil spray nozzles that lubricate the main bearings. They're the final defense against any particle reaching that critical surface. They can clog easily because they're so fine, but they provide that last layer of protection.
And the oil gets sprayed onto the bearings.
Yes, through precisely aimed oil jets or nozzles. They deliver an atomized spray or sometimes an air oil mist right where it's needed. The orifices are tiny, making filtration upstream absolutely vital.
What about air getting mixed in the oil? All that churning must create mist.
It does. That's handled by the Doiler, or air oil separator. It spins the air coming from the bearing vents, using centrifugal force to sling the heavier oil droplets out. The oil is collected and returned, and the relatively oil-free air is vented overboard.
Minimizes oil consumption.
And environmental impact.
And for checking engine health through the oil. Those magnetic things.
Magnetic chip detectors. Brilliant, simple devices. They're basically magnetic plugs placed in the scavenge lines or sumps.
You catch metal bits.
Exactly. They attract any ferrous, iron, or steel particles circulating in the oil. Technicians inspect them regularly. Finding metal chips is an early warning sign of wear or potential failure in a specific component, like a bearing or gear.
Allows for proactive maintenance.
That's the whole idea. Catch problems before they become catastrophic.
Lastly, on oil. What about the oil itself? Turbine oil characteristics. It's not regular motor oil.
Definitely not. It's a synthetic oil with very specific properties. High load-carrying ability for extreme pressures, must stay clean with minimal sludge or coking, must resist oxidation at very high temperatures, bulk stability, needs to be compatible with seals, especially carbon seals.
And compatible with other oils, but you probably shouldn't mix them.
Compatibility is usually required, but mixing different brands or types is strongly discouraged by manufacturers. Stick to the approved oil.
And safety. Handling this stuff.
Very important. Minimize skin contact wash thoroughly if you get it on you. Avoid breathing the vapors or mist for prolonged periods. Never ever siphon it by mouth. Use proper gloves and eye protection. And be aware that if the oil gets extremely hot, it can break down into potentially toxic substances. Treat it with respect.
Good advice. Okay, from oil to fuel. Fuel systems. These sound incredibly complex, too. What are their main jobs?
They have a lot to do. Precisely control fuel flow for power changes, automatically compensate for altitude and temperature changes, prevent flameouts either too rich blowout, or too lean flameout.
Right. Keep the fire lit, but controlled.
Exactly. Provide reliable starting and acceleration. And the nozzles need to atomize the fuel perfectly for efficient burning.
Who's the brain making all these decisions?
The Turbine Fuel Control Unit, FCU. Older engines used complex hydromechanical units, marvels of intricate valves and springs.
But now it's mostly digital.
Increasingly, yes. Modern engines use FAETC Full Authority Digital Engine Control.
FADEC. Heard that acronym a lot.
It's basically a dedicated computer system that takes inputs from numerous sensors all over the engine and aircraft throttle position, RPMs, temperatures, pressures, and calculates the precise amount of fuel needed second by second.
Full authority means it has complete control.
Complete electronic control. It optimizes performance, prevents exceeding engine limits, like temperature or speed, and makes the engine much more responsive and efficient. It's the standard now on new designs.
Makes sense. And fuel filtration. Just as important as oil filtration.
Arguably more so because fuel also acts as a lubricant for many fuel system components, like the high-pressure pump and parts of the FCU. Contaminated fuel can wreck these quickly.
So multiple filters again?
Yes, multi-stage filtering. Coarse filters at the inlet, very fine filters within the FCU, maybe 10 microns, screens after pumps. And just like the oil system, there are usually bypass valves.
So if a filter clogs.
The engine still gets fuel, albeit unfiltered, better than starving the engine of fuel entirely.
What about water in the fuel? That sounds bad.
Water is a major headache. It can freeze at altitude, blocking filters or lines. It doesn't compress, which can damage pumps. And it promotes microbial growth.
Bugs in the fuel tank.
Yes. Bacteria and fungi can live in the water that settles at the bottom of fuel tanks, feeding off the fuel itself. They create sludge that clogs filters and corrosive byproducts that damage tanks.
How do you manage water?
Regular draining of tank sumps is the first line of defense. Some filters can absorb a limited amount of water, and anti-icing additives often contain biocides as well. Keeping fuel clean and dry is crucial.
Okay. Now the fuel spray nozzles, they have to make a fine mist.
A very specific, fine, cone-shaped spray pattern. Good atomization is key for rapid vaporization and mixing with air, leading to complete combustion. It also ensures even temperature distribution in the combustor, preventing hot spots that could burn through the liner.
Are there different nozzle types?
Yes. Older engines used simplex nozzles, simple single orifice. They didn't atomize well at low fuel flows, like during starting or idle.
Okay.
Most modern engines use duplex nozzles. These have two separate fuel feeds. A primary orifice for low flows, start-idle, and a secondary orifice that opens up at higher flows, cruise takeoff. This gives good atomization across the whole operating range. They need a flow divider valve to manage the primary-secondary flow.
Makes sense. Any other types?
Air blast nozzles are also common. They use compressor air directed through swirl vanes right at the nozzle tip to help atomize the fuel even better. They often work at lower fuel pressures, which can allow for lighter pumps, and they tend to stay cleaner, resisting carbon buildup.
And those flow dividers are key for duplex nozzles.
Yes. The flow divider, or pressurizing and dump valve, senses fuel pressure and directs flow to the primary manifold first, then opens the secondary manifold as pressure, power demand, increases. It also often has a function to dump fuel from the manifolds at shutdown to prevent coking.
Coking, like burnt fuel deposits.
Exactly. Residual fuel baking onto hot nozzle tips.
Yeah.
Drain valves in the combustor also help clear unburned fuel.
Now, turbine engine fuels, how are they different from, say, AVGAS used in piston planes?
Very different chemistry. Jet fuel is basically kerosene. It's heavier, oilier, less volatile, doesn't evaporate as easily, has a higher boiling point and higher viscosity than gasoline. Its molecules have more carbon atoms. It's designed for continuous burning, not the explosive combustion of gasoline.
Does it have additives like car gas?
Yes. Often it includes inhibitors for corrosion, oxidation, icing, and microbial growth.
You mentioned volatility. Lower is generally better.
It's a balance. Lower volatility reduces evaporation loss and vapor lock risk at altitude, but too low makes cold starting harder.
So different types for different climates.
Kind of. Jet A and Jet A1 are the standard worldwide relatively low volatility. Jet B is a wider cut, more volatile, includes some gasoline fractions, used primarily in very cold regions like northern Canada and Alaska because it performs better at extremely low temperatures. More flammable, though.
How do you tell them apart? How do you prevent putting jet fuel in a piston plane or vice versa? Misfueling sounds catastrophic.
Again, it is catastrophic. Identification is key. AVGAS is dyed specific colors, blue for 100 LL, etc. Jet fuel is typically colorless or straw-colored. Fueling equipment is color-coded and clearly labeled. But the main physical prevention is nozzle size. The standard nozzle for jet fuel, a wide duckbill shape for over-wing fueling, or a specific round connector for single-point pressure fueling, is physically too large to fit into the smaller filler neck of an AVGAS tank on a piston aircraft. A simple but very effective safety design.
Brilliant. And purity concerns? Again, water and microbes are the main enemies.
They are the biggest contamination challenges. Water gets in mainly through condensation in tanks. As we said, it can freeze, cause corrosion, and allow microbial growth.
And the microbes make sludge.
Slime and sludge that clogs filters and corrodes tanks. Keeping water out through good fuel handling, sump draining, and sometimes using additives like fuel system icing inhibitors, FSII, which also have biostatic properties, is crucial. Sometimes direct biocides are needed if an infestation takes hold.
Okay, fuel system covered. Now, how do you actually get these massive engines started? Starting in ignition systems. There's a critical sequence, right?
Absolutely critical starting sequence logic. You cannot deviate. Step 1. Starter motor spins the compressor up to a minimum speed to establish airflow through the engine.
Get air moving first.
Must have airflow. Step 2. Turn the ignition system on. Get the spark ready.
Airflow, then spark.
Step 3. Only then introduce fuel. Airflow plus spark plus fuel, light off, and acceleration.
Why that exact order? What happens if you introduce fuel too early?
Big problems. If you spray fuel in before there's enough airflow, it won't mix properly or burn efficiently. You get a hot start. The exhaust gas temperature skyrockets past limits because the fuel burns too rich and slow, potentially melting turbine blades.
Ouch.
Or you might get a hung start, where the engine lights off but doesn't have enough energy or airflow to accelerate to its normal self-sustaining idle speed.
Yeah.
It just hangs at a low RPM, getting very hot.
So the sequence is vital for safety and engine health. The starter keeps helping for a bit too.
Yes, the starter usually stays engaged until the engine is well past the point where it can accelerate on its own, ensuring a smooth, reliable start up to idle speed.
What types of starters are used? How do you spin up something that big?
Several ways. Smaller engines might use a simple direct current DC electric motor. Slightly larger ones often use starter generators.
Dual purpose.
Exactly. Acts as a starter motor initially. Then, once the engine is running, it switches modes and becomes a generator to supply electrical power to the aircraft. Very common.
What about the really big engines on airliners?
They almost always use air turbine starters. These are small, powerful turbines driven by high-pressure bleed air.
Bleed air. Air from where?
It can come from a ground power unit, the aircraft's own APU, or even from another engine that's already running, a cross-bleed start. This high-pressure air spins the starter turbine at very high speed, which engages the engine's main shaft through a clutch mechanism,
What kind of clutch?
usually a Sprague clutch or similar overrunning clutch. It engages to transmit torque from the starter to the engine, but automatically disengages if the engine starts spinning faster than the starter, preventing the engine from driving the starter and damaging it.
Clever. Any older types?
Older military or some specialized engines used cartridge pneumatic starters. They could use bleed air, but also had the option of firing a pyrotechnic cartridge, basically a controlled explosion to generate gas pressure to spin the starter turbine. A bit more dramatic.
I bet. Okay, starter spins it, airflow is good. Then the ignition system fires. What type is common?
Almost universally, it's a capacitor discharge type system, high energy.
High energy. Why?
It produces a very intense, very hot spark. This is needed for reliable ignition, especially in cold weather or at high altitude where the air is thin and cold. It can easily jump the gap on the igniter plug and reliably light the fuel-air mixture. That high energy also helps burn off any carbon deposits on the plug.
So it's not like a car's ignition running constantly.
No, usually it only operates for a short period during the start sequence. Once the flame is stable and continuous in the combustor, the ignition is typically switched off.
Although sometimes they use continuous ignition.
Yes, in certain conditions like takeoff, landing, heavy rain, or turbulence, or when flying near stall speed, pilots might select continuous ignition, usually at a lower energy level, as a safety measure. Just in case the flame were to blow out, it would relight immediately.
Okay. And the igniter plugs themselves, different from spark plugs.
Yes. They look superficially similar, but are built differently. They handle much higher energy. They have a much wider gap between the electrodes because the pressure inside the combustor during start is relatively low, making it easier for the spark to jump. And because the spark is so intense, they are much less prone to fouling than traditional spark plugs.
Good to know. And finally, ignition system maintenance safety. Sounds like there's serious voltage involved here.
Extremely serious. These capacitor discharge systems store a lethal amount of electrical energy in the exciter box, even after the power is turned off.
Residual charge.
Yes. Accidental contact with the igniter lid connections can be fatal. The absolute rule is always disconnect the lead at the exciter box end first. Never touch the connector pins. Use insulated tools. Follow the maintenance manual procedures precisely. You cannot be too careful around these systems.
Definitely noted. Wow, okay, that covers the essential support systems. Now, Section 4, monitoring, maintenance, and longevity. How do we keep tabs on these complex beasts in flight, engine indicating systems?
Right. The cockpit displays give pilots the engine's vital signs. Temperature monitoring is probably the most critical.
EGT, TIT, TGT, lots of acronyms. What are they measuring?
They all refer to measuring the temperature in the hottest part of the engine, usually around the turbine section. EGT, exhaust gas temperature, is common, measured just downstream of the turbine. Sometimes it's TIT, turbine inlet temperature, TGT, turbine gas temperature, ITT, interstage turbine temperature, or TOT, turbine outlet temperature. The specific name depends on where the sensors are located, but the goal is the same. Monitor the temperature of the hottest parts to prevent exceeding limits.
How do they measure such high temps?
With thermocouples. These are junctions of two dissimilar metals that generate a small voltage proportional to the temperature difference between the measuring junction in the hot gas stream and a reference junction. Multiple thermocouples are usually spaced around the engine casing, and their readings are averaged to give a single display value.
Okay. Another key gauge seems to be engine pressure ratio, EPR. What's that showing?
EPR is a ratio. It compares the air pressure at the very inlet of the engine, PT2, to the pressure at the turbine exhaust, PT7.
Inlet pressure versus outlet pressure. Why is that useful?
On many large turbofan engines, EPR is the primary indicator of how much thrust the engine is actually producing. It's a more direct measure of thrust than RPM in many cases.
Wow.
Pilots use the EPR gauge to set the precise thrust needed for takeoff and other flight phases.
Got it. And tachometers for RPM, measuring how fast things are spinning.
Exactly. They measure the rotational speed of each main rotating spool, since most turbofans have two spools, or sometimes three.
N1 and N2.
Right. N1 is the low-pressure spool, fan and low-pressure compressor turbine, and N2 is the high-pressure spool, high-pressure compressor turbine. Each has its own tachometer gauge.
And they're shown as a percentage.
Yes, usually calibrated in percent RPM. This makes it easier to compare engines and avoids dealing with huge numbers like 15,000 RPM. 100% RPM usually corresponds to the engine's maximum rated speed for takeoff.
How do they measure RPM? Electrically?
Often, yes. Small AC generators driven by the engine spool where the frequency of the AC output is proportional to the speed. Or sometimes probe-type sensors that detect the passing of gear teeth or blades magnetically, generating pulses. These have no moving parts and are common inputs for FADC systems.
What other critical indicators are watched closely?
Fuel flow is very important, usually shown in pounds per hour or kilograms per hour. Pilots constantly monitor it for fuel management and to check engine performance.
Why pounds per hour, not gallons?
Because fuel weight is what matters for aircraft weight and balance and performance calculations, not volume.
Makes sense. What else?
Oil pressure and temperature are vital for the lubrication system's health. Oil temperature especially indicates if the oil cooler is working properly. And vibration monitoring.
How important is vibration?
It's become increasingly important as a secondary health indicator. Sensors, usually piezoelectric accelerometers, are mounted on the engine casing to detect vibrations from the N1 and N2 rotors.
What can it tell you?
An increase in vibration can indicate an imbalance, maybe due to fan blade icing, FOD damage, or even an impending bearing failure. It helps pinpoint which engine might have a problem and supports condition-based maintenance.
Okay, lots of data coming into the cockpit. How is this used for engine monitoring and troubleshooting on the ground?
During ground runs after starting, technicians do careful engine checks. They verify oil pressure rises within limits, RPM stabilizes at the correct idle speed, and EGT is within the expected range. Everything needs to look normal before proceeding.
And setting power for takeoff.
Takeoff thrust setting is critical. As we said, EPR, or N1 RPM, is used. But thrust output is very sensitive to ambient air temperature and pressure altitude. Hotter air or higher altitudes mean less dense air, which reduces thrust.
So pilots adjust for that.
Yes, or the FADEC does it automatically, calculating the exact EPR or N1 target needed for the current conditions to achieve the required takeoff thrust. Interestingly, humidity has very little effect, so it's usually ignored.
What about engine shutdown? Anything special there?
Yes, the cooldown period. If the engine has been running at high power, it's crucial to let it idle for a few minutes, typically 3 to 5 minutes, before shutting it down.
Why? What happens if you shut it down hot?
The internal parts, especially the heavy turbine discs, cool down much slower than the engine casings. If you shut down immediately, the casing can shrink faster than the rotating parts, potentially causing the turbine blades to rub against the shroud or even seize the rotor. The cooldown allows temperatures to stabilize.
Good tip. And shut off the fuel boost pump after the engine fuel lever.
Yes, ensures the engine-driven fuel pump doesn't run dry as it relies on fuel for lubrication.
What are some common malfunctions seen through these indicators?
If you see high or low EPR, it might be faulty probes, leaks in the sensing lines, or bad transmitter indicators. High EGT is always a worry, could indicate turbine damage, compressor issues, problems with accessories dragging the engine down, bleed valve issues, or the engine just needs adjustment, trimming. High vibration, as mentioned, usually points to rotor imbalance from icing or damage.
And for digging deeper, there's SOP, spectrometric oil analysis.
Yes, SOP is a fantastic proactive tool. You take a small sample of engine oil periodically and send it to a lab.
Like a blood test for the engine.
Exactly. The lab uses a spectrometer to analyze the oil for tiny traces of wear metals, microscopic particles of iron, copper, chromium, aluminum, etc., measured in parts per million.
What does that tell you?
Different metals come from different components. If the level of, say, silver starts rising, it might indicate wear in a silver-plated bearing. An increase in iron might point to gear wear. It allows maintenance teams to detect abnormal wear before a component fails, enabling targeted inspections or replacements. It's predictive maintenance at its best.
Amazing insight from just the oil.
Mm-hmm.
And for actually looking inside without taking it apart.
That's the borescope inspection, essential tool. It's a thin probe, either rigid or flexible fiber optic, often with a camera on the end, that can be inserted through small access ports in the engine casing.
Like keyhole surgery.
Pretty much. Allows technicians to visually inspect internal parts like compressor blades, combustor liners, and turbine blades for cracks, burning, erosion, FOD damage, or other issues. Saves a huge amount of time and effort compared to disassembly.
Invaluable. Okay, let's get into the actual maintenance deep dive, starting with the compressor section. What's the main issue there?
Dirt accumulation. Compressors ingest huge amounts of air, and that air isn't perfectly clean. Dirt, dust, pollen, salt spray near coasts, oil fumes, it all builds up as a coating on the blades and vanes.
And that hurts performance.
Significantly.
Huh.
Just like ice on a wing disrupts airflow, this layer of grime reduces the aerodynamic efficiency of the compressor blades. The engine becomes less responsive, slower to accelerate, and runs hotter, higher EGT, for a given thrust setting.
So how do you clean it? Can't just wipe it down.
Two main methods for cleaning. First is compressor washing. You motor the engine over with the starter, ignition off, and spray a mixture of water or a special cleaning fluid into the inlet. It washes the deposits off the blades as it flows through.
Okay, an internal shower.
Pretty much. The other method is grip blasting. Here, you run the engine at a low power setting and carefully inject a mild abrasive grit, often ground walnut shells or apricot pits, into the inlet.
Grit. Doesn't that damage the engine?
It's a carefully controlled process using soft grit. The grit scours the deposits off the compressor blades. It's designed to be completely burned up when it passes through the hot combustion section so it doesn't harm the turbine. It's effective, but only cleans the compressor.
Got it. What about minor blade repair? Nicks and dents.
Small nicks and dents on axial compressor blades can often be repaired by carefully blending them out with fine stones or files. The goal is to remove the sharp edges, which act as stress risers where cracks could start, leaving a smooth finish. Minimum material removal is key.
But cracks are a no-go.
Absolutely no cracks allowed. Any crack found on a compressor blade means the blade must be replaced. Period.
Which brings us back to FOD prevention. Constant vigilance.
Constant. Turbine engines are like vacuum cleaners. They will suck up anything loose near the inlet tools, nuts, bolts, rivets, safety wire, pens, badges, ramp debris. Technicians must have meticulous tool control, clean work habits, and always check the inlet area before and after maintenance. Ramp sweeping is also vital. FOD damage is incredibly expensive and dangerous.
Okay. Moving to the back. The hot section inspection. Combustion and turbine. Critical area.
The most critical, due to the extreme temperatures. The condition of the hot section dictates engine life and safety. Regular inspections, often using borescopes, are paramount.
What's the main thing you look for?
Cracking is the most common discrepancy. Cracks in combustion liners, especially near edges or welds, cracks in turbine nozzle guide vanes, and cracks in turbine blades or discs are all serious findings. Maintenance manuals have very specific limits for allowable crack types, sizes, and locations. Many cracks require immediate component replacement.
What about turbine blades specifically? They take the most abuse.
They get intense scrutiny. We look for stress rupture cracks, which are fine cracks often running perpendicular to the blade's edge, caused by the combination of heat and centrifugal force over time. We also look for signs of overtemperature, like blade tip curling, distortion, waviness, or changes in the blade's thickness or airfoil shape. Any sign of overheating is a major concern. Wear on the blade tip shrouds is also checked.
And they're installed in balanced sets.
Yes, turbine blades are precisely weighed and installed in balanced sets around the disc to minimize vibration.
Clearances are also critical back there.
Extremely. The gap between the rotating blade tips and the stationary outer shroud or casing must be precisely maintained. Too tight, and they rub. Too loose, and efficiency drops significantly as gas leaks over the blade tips. Measured with feeler gauges or specialized tools during assembly and inspection.
And hot spots on the outside, on the tail cone.
Yeah, discolored or blued areas on the exhaust cone can indicate uneven burning inside, possibly due to a clogged or malfunctioning fuel nozzle or a problem within a specific combustor can. Needs investigation.
Okay, that's inside the engine. What about power plant installation? Details how it connects to the plane. The firewall.
The firewall is that non-negotiable fireproof barrier between the engine nacelle and the aircraft structure, wing or fuselage, usually stainless steel or titanium, designed to contain an engine fire for a specified period.
The cowling or nacelle.
That's the aerodynamic fairing around the engine. Protects the engine, smooths airflow. Made of fixed and movable panels, often hinged for maintenance access, usually aluminum or composite materials.
Acoustic panels we mentioned for noise.
Yes, those sound-absorbing liners fitted inside the inlet and fan ducts. Porous face sheet, honeycomb core, Adds weight, but significantly reduces noise.
Engine mounts, how are they attached?
Usually robust forged steel or titanium mounts that bolt the engine casing to the pylon or aircraft structure, designed to handle massive thrust loads, torque, and gyroscopic forces while allowing for thermal expansion. Typically 2 main mounts at the front midsection and 1 at the rear for stability.
Fluid lines, hoses, and pipes. Strict rules for these.
Very strict. For rigid metallic tubing, always replace with the same size and material. Bend carefully with proper tools to avoid kinking. For flexible hoses, like braided steel or Teflon, use the exact same part number, size, and length. And crucially, always install with 5/8% slack. Never install a hose stretched tight or with sharp bends. It needs freedom to flex with engine vibration and movement, otherwise it will fail quickly. Don't twist hoses either.
Good tip on the slack.
Yeah.
And O-ring seals. Those little rubber rings.
Found everywhere, sealing fluid connections. The absolute golden rule, never reuse an O-ring. They swell, take a set under pressure, get nicked or damaged invisibly. Always replace with a new one of the correct material and size, properly lubricated. Store them correctly too, away from heat and light. Cheap part, critical function.
Wiring looms and connectors, how are they routed?
Carefully routed to avoid chafing against structure. Clamped securely to prevent vibration damage. Protected where they pass through bulkheads using grommets. Should avoid hot areas in places where they could be used as handholds or steps. And importantly, form drick loops before connectors.
Just loops.
Yeah, a small downward loop in the wire just before it enters a connector or junction box. Any moisture or fluid running down the wire will drip off at the bottom of the loop instead of wicking into the connector and causing shorts or corrosion. Simple, but effective.
Clever. What about drains, places for fluids to escape?
Yes. Various drains are built into the nacelle and engine systems for oil breathers, fuel pump seals, thrust reverser actuators, etc. They allow normal leakage or overflow to drain safely overboard. Important maintenance check is to ensure these drains aren't blocked.
And lifting the whole engine. Use designated lifting points only.
Absolutely. The engine manufacturer specifies exact points on the engine casing designed to take the load for lifting during installation or removal. Using any other point can severely damage the engine structure. Hoists and slings must be attached correctly to these points.
Makes sense. Lastly, fire protection systems. How are engine fires detected and fought?
Detection first. Systems use various detection types. Could be spot detectors, like thermal switches that close a circuit at a set temperature, or thermocouples. More common on transport aircraft are continuous loop systems. These are long sensor tubes routed throughout the engine nacelle.
How do they work?
Different types exist. Some have 2 wires embedded in a special material, eutectic salt, whose resistance drops dramatically when heated by a fire, triggering an alarm. Others contain a gas-filled core. Heat expands the gas, closing a pressure switch. They provide more comprehensive coverage than spot detectors.
Can they be tested?
Yes, system testing is usually done from the cockpit. Test circuits simulate the overheat or fire condition, example, by passing a current through the loop to heat it slightly or simulating the resistance change, verifying the integrity of the loop and the alarm function.
And if a fire is detected? Extinguishing systems.
Fixed extinguishing systems are installed. Requirements vary. Smaller commuter planes might need 1 shot. Large transport aircraft require 2 discharges per engine. APUs often have automatic discharge capability on the ground.
What do they spray? Foam.
Usually not foam in an engine nacelles. It's typically an inert agent, like halon, though being phased out for environmental reasons, or newer replacements like Halotron or Fe36. These agents work by chemically interrupting the combustion process or by displacing oxygen, smothering the fire.
And the fire switch or handle in the cockpit, what does pulling that actually do?
Pulling the fire switch for a specific engine initiates a critical sequence. It isolated that engine, closes the main fuel valve, spar valve, shuts off hydraulic fluid to the engine-driven pump, trips the engine's generator offline, cuts power to the thrust reverser, basically walls off the engine from the aircraft system.
Isolate it completely.
Then, rotating or pushing the switch, depending on design, fires the extinguishing agent squib, discharging the bottle into the nacelle. If there are 2 bottles, the switch can usually select which one to fire or fire the second one if needed. It's a very deliberate multi-action sequence.
Incredible integration. Okay, final topic. Engine storage and preservation. Why is this necessary? Can't you just park an engine?
Not if you want it to work again. Corrosion is the enemy, especially internal corrosion. When an engine sits idle, especially in humid air, moisture can condense inside, and dissimilar metals can start galvanic corrosion very quickly. Preservation aims to prevent this.
Are there different levels of storage?
Yes, based on duration. Active storage is short-term, maybe up to 30 days, often just requiring the engine to be run periodically to keep oil circulated and moisture out. Temporary storage, 30 to 90 days, requires more steps. Indefinite storage, over 90 days or removed from aircraft, requires the most thorough preservation.
What corrosion preventive materials are used?
Special lubricating oils mixed with corrosion preventive compounds, CPCs. These coat the internal surfaces. They are not the normal operating oil and must be flushed out before returning the engine to service. Different types exist for different durations and components.
What about moisture already in the air?
Dehydrating agents or desiccants, like bags of silica gel, are placed inside engine openings and compartments to absorb atmospheric moisture. Openings are sealed with plugs and covers.
And for long-term shipping or storage? Special containers.
Yes, engines are often sealed in large, airtight plastic or foil bags, sometimes with desiccant inside, or placed in dedicated shipping containers. These can be sturdy wooden crates or sealed, sometimes pressurized metal containers.
How do you know if the protection is working inside a sealed container?
Monitoring. Humidity indicators are usually placed inside the container or bag. They change color, for example from blue to pink, if the relative humidity gets too high, indicating the desiccant needs replacing or the engine needs represerving. Pressurized containers have gauges to check for pressure loss. Inspections are done periodically according to the storage procedure.
It's a whole science in itself, just putting an engine to sleep properly.
It is. Proper preservation saves enormous costs down the line by preventing hidden corrosion damage that could lead to failure when the engine is put back into service.
What an absolutely fascinating journey. We've gone from basic physics, Newton's laws, right through the intricate anatomy, inlets, compressors, combustors, turbines, exhausts, explored the vital support systems like oil and fuel, and then covered how we monitor, maintain, and even store these incredible machines.
Yeah, it's a lot to cover, but hopefully you now have a much deeper appreciation for what's going on inside that pod hanging under the wing. It's not just brute force, it's layer upon layer of incredibly clever, precise engineering.
You definitely get a sense of that interconnectedness, how each part relies on the others. It really goes beyond just knowing facts. It's about understanding the why and the how.
Exactly. And seeing how rigorously the aviation industry, through standards like ES Part 66, approaches the design, operation, and maintenance of these complex systems is quite something. The focus on safety, efficiency, performance, it's relentless.
It really is. And that leads to a final thought for you, our listeners. We've seen this incredibly detailed, systematic approach applied to gas turbines. So here's something to ponder. How could applying that same kind of rigorous systems thinking approach, that deep methodical dive into understanding complex interconnections, benefit other complex engines in our world?
Interesting question. You mean like applying aviation-level system analysis to things like healthcare delivery,
Wow.
or managing global supply chains, or maybe even tackling complex environmental challenges?
Precisely. What other complex systems could be better understood, managed, or improved if we approach them with the same depth of analysis and focus on reliability that goes into ensuring every single flight is safe and efficient? Something to think about.